Good morning. Okay, so we're in this part of the discussion, we're going to back off a little bit of the YCAG research aims and discuss a couple of projects that we've been involved with various state and local communities. This isn't our only interaction, but these are the two sort of most recent actually that have quite a bit of data support. Most of this work is done by us either gratis or usually there's a give and take. So with some of the organizations, if there's a research aim that we can also achieve at the same time as providing data to answer more management questions, then we're happy to get involved. Obviously, we stay away from just doing private sector service work. That would certainly be an aim, potentially. But at this stage, there's always a research goal in mind from any of our involvement in these projects. So we'll go ahead. And the first project is fairly recent, just completed from our end not that long ago in the spring. And basically, we were asked to assist the city of Laramie to locate the Sherman Hills Fault Zone in advance of monitoring well drilling, essentially. And then after that drilling took place, we were asked to help characterize the petrophysics or the geophysical properties within the rocks with borehole geophysical logging and help the groundwater assessment that was going on with this borehole geophysics. So what we're going to look at a lot, unfortunately with the time I have, I'm really just going to go straight to results. So we're not really going to discuss a lot of the details of what we did and how we did it, but we're just going to go straight to what matters. So let's suffice it to say that this was a two-pronged investigation from our end, right? There was the pre-drilling work and the post-borehole assessment. So we use seismic refraction and electrical resistivity first in an area that is of interest to the city. It's on the border basically between the city of Laramie's influence and the Albany County land. And additionally, the property here that's shown by sort of that blue ovoid is actually foundation property. So it's university property. So adjacent to the site of interest for the city, which is will be a park at one point here called Imperial Heights Park. The foundation owns property, which allowed us to actually collect data with really ease, since there's very little permissions required other than talking to the foundation. So we know from geologic mapping that the Sherman Hills Fault traverses this area. The question was exactly where and how would that impact sort of the monitoring well establishment or the establishment of those holes or the drilling program. So in the fall of 2014, oops, hitting the wrong button here, excuse me. We basically acquired a seismic refraction profile and an ERT profile along these two zones. I'm only going to show you the longer of the two, it's just from a time standpoint. And generally, again, if this is Laramie, we're on the very sort of southeastern portion of the city. So the very border basically between city property and county property. We'll go straight into what we saw and the interpretation that was put on top of it. This is the electrical resistivity. Our hot colors are more resistive materials, therefore less apt to show higher porosities or potentially less likely to be clay-dominant topologies. The thing to note really is this offset between the resistive blocks that this seems to be higher than this block, which is in line with the interpretation of the actual movement across the Sherman Hill Fault. The other interesting thing to note from the electrical resistivity is the appearance of a zone that's fairly narrow. This distance scale is in meters. That looks like it's a lower resistivity. cooler color there as a lower resistivity. So that either infers that this fault zone is a clay-rich environment, or potentially there's a fluid contribution in that zone, lowering the background resistivity. Now, if we look then at the similar seismic data, as we've been discussing with all the YK research, fracture intervals can lower the seismic velocity whether they're actually filled with a fluid or not. And in itself, the seismic again sort of highlights that same area as potentially the fault zone itself. So in itself, the data is useful to help locate the monitoring drilling, right? And that's basically what happened. Now, details of the fault were refined. Essentially, the plan, and again, I'm not the most knowledgeable about the city monitoring plan, but nonetheless, well, I'll do my best to explain what I understand of it. But in the early spring of this year, the city contracted drilling for 4 monitoring holes, and they are shown here, really small, unfortunately. So you can see the trace of the Sherman Hill Fault. So in this zone, which is where the Imperial Heights Park is, 3 wells were drilled. The north well, the assumption was it would be on the northern side of the fault zone, a middle well in the fault zone, and then the southern well on that southern end, the down-thrown block, essentially. Additionally, another well, which was called Triangle Well, actually near Walmart, was also drilled. And what we're going to focus on is the borehole geophysics related to one of those holes. Now, all 4 of those holes were geophysically logged with every tool YK possibly has, which again, I need more time if we were going to discuss every one of those things. But let's suffice it to say a lot of data was collected and presented to the city and the groundwater specialists who were looking at the rocks and the fractures in those boreholes. So, and all this information that I'm talking about now basically comes from a report that you can look at online with the city of Laramie. So this was already a presented report. So if you're interested, you can get some more information there. Basically, we have the Casper Aquifer that the city of Laramie uses. This is a cartoon of the stratigraphic situation, and the areas of interest really are the upper levels of the Casper, which are named the Epsilon and the Delta. As you can see on this cartoon, the city of Laramie Springs, so where we get our city water half the year, is basically indicated here. That Imperial Heights area is basically shown stratigraphically right about here. So the concern is that if there is any tracers of interest, whatever one you might want to pick, potentially they will go directly into these aquifer units, and based just on a topographic interpretation of how groundwater moves, they're going to move potentially into wells that the city cares about. This is another way to look at that same explanation. So these are wells and water elevations in those wells with inferred groundwater movement pathways, all right? The important thing here is here are our 3 wells, the north, middle, and the south. Here's our triangle well, and here's the city source wells. Okay, so everything essentially that happens here will be predicted to move towards what we care about. All right, I can only pick a little bit of this data again, so we're going to look at the triangle well, the one near Walmart. We're going to look at 2 aspects of it. What we're seeing here is the caliper log, so just a measure of the borehole diameter and depth. You can see this is in metric here, so we're basically going from the surface or just below the casing level, which is great. Casing is to about 30 odd feet, 40 feet roughly, and then all of this is open hole. You can see these large sort of spikes going out. That represents breakouts of fractured intervals within the Casper sands and limestones. This next figure over here, which is really hard to see, is actually the optical televiewer view of the sidewall of the borehole. So most of this sort of lighter yellow color and darker red color are the sandstones within the epsilon and the delta. These lighter zones that you can see here, or this darker zone here, are limestones within that sort of separate those sandstones. And then these curves, lastly, that are shown here, this blue line and this red line, actually are the flow going up the borehole and or down the borehole at various steps. So let's suffice it to say that these curves represent how much water is coming into the hole and leaving the hole. All right, and if we pick, say, the red curve, for example, we can see that this scale is in gallons per minute. You can see at this particular level, around 120 odd feet below the surface, we have roughly 30 gallons, well, say 20 gallons per minute coming into that borehole through fractures. As we go up another sort of 6 meters roughly, or maybe say 20 feet, we add another 10 gallons per minute also into the borehole flowing up. This would actually be the delta member, the delta sand, providing that water, which then flows up the hole and then leaves almost entirely through another fracture in the epsilon. All right, so we're looking at vertical dynamics of the groundwater flow here. If we look in detail at that particular well, and we relate it also to the groundwater tracer work that was done, and the tracer of note here was nitrate, we can see those 3 fractured intervals. So the lowest one that produces about 20 gallons a minute into the hole, the next one up, which adds another 10 gallons per minute, and then that hole higher up in the section, around 90 feet or so, that actually takes most of that water away. So these 2 fractures are in our delta sandstone. This one is in the epsilon. Okay. Now, normally, without this borehole, this limestone would be separating those 2, and anything within the delta member here, the delta sand, wouldn't be traveling into the epsilon. So it's a little bit of a concern, especially as we look at the nitrate levels within the delta, which are shown here and are elevated. And then as the testing was going on for those actual tracers, you can see that without this connection, that nitrate level was lower. So we're basically taking higher nitrate water from the delta and moving it into the epsilon. Now, this may look really bad, right? Well, fortunately, as we speak, these wells are being capped and changed. So this is a monitoring situation to understand movement, not only laterally, but vertically. So the next part of this whole study then was to look again at the fault zone itself, to say how transmissive is this fault zone? Does groundwater move across the Sherman Hill Fault, or does the Sherman Hill Fault act like a barrier? If we were just looking at our resistivity profile again in the low resistivity zone that seems apparent, we might throw out a guess that it is a barrier to flow. Otherwise, we might expect the resistivities to be higher, but obviously that these data by themselves don't answer that question uniquely. So a pumping test was done across the north, middle, and south wells. The pump was in the north well and basically pumped 400 gallons a minute for 2 days, and there was drawdown, obviously, across the middle and across the south, which helps us at that point establish that this fault zone does pass water when stressed. Okay, that's a good thing to know, and just put a period right behind, right? So there's no more question of the Sherman Hill Fault acting like a zone that could potentially barrier any contaminant movement towards the city holes. All right, it can't do it. If it's under enough pumping stress, water will move across that zone. Okay. Now, this is a summary of the nitrate levels that were monitored, or that were sampled in these holes. Again, you can refer to the city's report from June. Again, there was an adjustment here for the same flow lines that were shown earlier and inferred earlier, but with color coordination for the nitrate levels. So obviously the takeaway from this study that we in YK helps provide science to was that higher nitrate levels, are found here and in theory could easily move across the fault zone and start to impact potentially the Turner well field or the city wells. Now, I'll leave it at that. So certainly we're providing science to the managers and to the groundwater people, the groundwater modelers, directly, that can help support and refine the estimates of where this water is actually going. Okay, now, next project that we'll quickly go through, and really quickly, was done about the year before. It was another collaboration between YPEG FINS, or the geophysical side of YPEG, another company, Wyoming Groundwater, who is actually associated with the first one as well, and the State Water Development Commission. So this was actually their project for a town called Manville, which is up by Lusk, for those that aren't familiar. And then this site, basically the questions required us to implement a seismic reflection, a deeper resistivity program, and some surface NMR. So we'll just really quickly go through what was learned there. So just in general, Laramie's down here where we're all sitting, Manville's up here near Lusk. Basically the questions were, how do we, and they were groundwater related, let's back up a second. So there was no real look at surface hydrology. Again, this is not exactly our research aims for YPEG. This was a deeper understanding of groundwater and groundwater potential. So, are there any drilling potentials for groundwater in the Hartville? All right. Currently, the city of Manville, which is a very small city, or maybe town would be a better way to refer to them, source water from the upper 100 feet. Okay. They were having issues in that the uranium levels within that current city well were above EPA standards, therefore they had to move that well. They had to source their water somewhere else. The question was, if you go deeper, meaning about 600 feet instead of 100 feet, could you find better water? No one had even remotely addressed that question yet. And the second part of that was, could the subsurface structure of the placement for the new well influence higher levels of uranium also? So what was the basic geologic structure? What was the background? Could the new well placement, regardless, start to see higher uranium levels as well? So two basic questions, very research oriented and very applicable to a deeper geophysical application of the same methodologies that we've been talking about already, that have been applied mostly to the very, very near surface. So just to give you a really, really quick overview of the geology roughly in the Manville area. Well, oopsies, let me back up again. The town of Manville sits here basically on top of the Arickaree, and then there's a sliver of this White River group, which is mostly a shale dominant unit, sitting on top of Hartville. And we can think about Hartville in a lot of ways like we think about the Casper. So a sandstone, limestone, dominant lithology mix, good potential for a groundwater aquifer. Currently, the city or town of Manville sources about this border zone, so the very base of the Arickaree. There's a cobbly layer where they pull out their water. Excuse me. So, what did we do? We did some preliminary seismic reflection to look at the basic structure of the lithologies and how they interrelate. The current well for the town sits here right in town, and the newer well is actually quite a ways out. You'll see we also did an NMR sounding right at the new well just to get a better idea of what the saturation levels were at that particular drilling site. And the seismic was done over quite a limited area, so in two little patches, really due to just time and basic understanding of what the structure will be closer to those areas. Now, the electrical resistivity, though, was done over this entire 2-mile section, right? And the target for the resistivity was much deeper, say the Hartville, which starts at about 600 feet. So the resistivity sections that we'll see for this line are much, much deeper than anything we've looked at to date with the research that YK currently does. First, we'll just look at the results for the NMR. This was a really challenging NMR site. This was mainly led by, again, Brady Flincham of Steve's group. And we were paralleled on both sides by electrical lines and an active highway. So to get any sort of data that's useful was pretty amazing. The parts to focus on really are this area of the T2 curve, which is basically an increase in the water content at the base of the aurifery, which is no surprise given that's where they currently get their water anyway. What was a little bit of a surprise that in the White River group, actually, we have this zone that also sort of gives us a higher water content that isn't just due to the clay presence. All right, and during the drilling, at first when we saw this was a little bit anomalous and not really sure what was going on until I was discussing things with the groundwater hydrologist, or hydrogeologist really, and we talked about the drilling, and there was a cobbly zone at that level in the aurifery, in the White River group, which did produce a small amount of water. So it does show some sensitivity of NMR to the water presence even within a clay-dominant sequence, which is very encouraging for other potential study sites that we might encounter. Structurally, this is just a snippet of the seismic reflection data. The thing that strikes right off the bat is the fact that there's a lot of sort of structure here. This isn't just a layer cake basin as one might normally expect, or as what I expected. There appears to be a lot of normal faulting shown in the data as one progresses from the north towards the south. It's just also the direction towards what's called the Hartville uplift, which is a granitic intrusion in that neck of the woods. So there is a lot of structure. The faulting wasn't previously understood quite as well. There were a lot of map surface faults from basic geologic mapping, but yet the scale hadn't been quite refined as well, and these small little reflections profiles actually do a little better job. So if, again, one was looking to site new well development, you might either want to follow some of these fractured zones or avoid them potentially, depending on whether you think they're more clay dominant or actual transmissive zones for better water from deeper levels. And finally, what we'll look at here is the resistivity profile, again interpreted. So there are no boreholes, let me start off by saying, that go deep enough in this particular area for calibration of either the seismic data or the res data, so this is truly interpretation. But it does show two primary things in that we do have capability to look to 800 odd feet with our resistivity system if we're so inclined. Again, that's a very large scale, much larger than anything we've been talking about with our near surface studies in YK. But nonetheless, there's some bulk features that are rather interesting. First bulk feature is these geologies are interpreted from the wells that are available, so there's only really two. And that first one, the one that's most useful, is right here near the new city well, and it actually goes into the Hartville and actually loses circulation even. So this whole resistive part of the Hartville tends to be reasonably well constrained, or at least in our interpretation, because we know from drilling this hole that there was a loss of circulation right at that depth. The interesting thing is there is definitely fault movement in the Hartville from the southern part of the line to the northern part of the line. Again, does that mean this fault zone is connected or not? Not really sure. I would say it's less likely that water moves across that fault zone, given that the Hartville on the north side of the fault tends to be saturated and of a lower resistivity more than likely than the same units over here, which tend to be higher resistivity. Again, purely interpretive, but useful if the town or the state decided to sink a 600-foot hole for water at Anvil. Probably you'd be more inclined to drill that hole over here than you would over here. Okay, and with that, I'll leave you. If you have any questions, hopefully I'm still going to talk. One question?
So Brad, I'm very interested in whether or not the uranium that is appearing in Manuel's water must be from roll fronts coming off the old Tarpeville granite. Is that where that is coming from?
As far as I'm aware, that's the understanding. So I think and this again is kind of my understanding as of about a year ago, because I haven't really been actively involved with that, and maybe if there's any of the Development Commission folks here, they could help illuminate. But as far as I understand it, the Orickery and the White River especially are depositional uranium units that already on their own, regardless of sort of roll front mining and things like that, or deposition, they were probably depositional units from sort of the Jeffrey Mountain area, sort of that central Wyoming area where there's sources of more uranium.
So does that mean that if you were to advise the Development Commission, you'd say that you've got to get below those areas that are potential roll fronts to get away from uranium?
Yes. Well, that would be, without having any groundwater sampling data to support that, I mean, it seems like a logical conclusion that your better water would be deeper.